Welcome to the third week of the course Unit Operations in Particulate Matter. This is the first lecture of week 3 and here we are covering topic fluidization. Now this topic fluidization will be covered in two lecture 1 and lecture 2. In lecture 1 what we will discuss? We will define the fluidization, we will discuss different types of fluidization and then characteristics of fluidization will be discussed. Lecture 2 we will cover governing equations associated with the fluidization process. So, let us start the lecture 1 of week 3 and here we will define the fluidization. So, what happens when a fluid is passed downwards through a bed of solids, no relative movement between particles takes place unless the initial orientation of particle is unstable. Now, what is the meaning of this statement? For example, if I consider a column where particles are available, where the column is filled with the particles. Now, if fluid enters from the top and moves downward, then what happens? When it will pass through the particle, it will not disturb the movement of the particle until unless the orientation of the particle will be changed. For example, if I am having a very needle kind of particle and if particle initially associated like this, so when fluid will pass through this, it may be oriented, it may take position vertically. So, in that case, if this type of orientation of different particle occur, then the position, then the bed, then the height of the bed may change, but it is not significant. On the other hand, what happens if the fluid moves upward? Initially we have discussed the movement of fluid towards downward. Now we will discuss what happens when fluid moves upward through the bed of particles. So, when a fluid is passed upward through the bed and if the frictional drag on the particles become equal to their apparent weight. What is apparent weight? Is the actual weight minus the buoyancy force. The particle becomes rearranged, thus offering less resistance to flow of the liquid and the bed starts to expand with a corresponding increase in voidage. Now, what happens when fluid moves from downward through the bed of particle? It exerts a drag force on the particle. Now, if that drag force will be equal to the apparent weight of the particle, it means the weight of particle itself minus the buoyancy which is acting over this. When this difference of this will be equal to drag force which is exerted by the fluid, it will leave its position and start moving upward. So, at that point the height of the bed expands or height of the bed increases, and when height of the bed increases, the voidage available between the particle that also increases. Further, this process continues with the increase in velocity with the total frictional force remaining equal to weight of the particle until the bed has assumed its loosest stable form of packing. So, what happens? Further increase in velocity further allows particle to leave its stable state and go for the moving state. And when we further increase the velocity, the individual particles separate from one another and becomes freely supported in the fluid. So, what happens when all forces forces acting on the particle like weight of the particle itself and buoyancy force and drag force, when drag force is equal to the apparent force of the particle, what happens? It will start leaving its space. Now, when we further increase the velocity, it will lose its stable condition and it will be carried by the fluid. So, in that case we can say that particle is supported by the fluid. Now, when the particle will be supported by the fluid, it means it will leave its space and moving with the fluid. So at that position, at that time when the particle moves, what we call this, the particle is at fluidization condition. So that when the particle start moving with the liquid, we call this fluidization, and that state is entirely different when the particle is at a stable position. Now if you see this graph, this is drawn between height of the bed versus velocity. Now what happens, as we have discussed, that particle will remain at a stable position till velocity will increase, and that velocity will put the drag force, and then when this drag force is equal to the apparent weight, till the particle will stay at stable condition. So when velocity will increase, you see in this graph, when velocity will increase, we are observing the effect on pressure drop and effect on bed height. Now pressure drop increases, you see in this graph shows with the increment of velocity, pressure drop increases till all forces become at equilibrium. All forces means drag force should be equal to weight of particle minus buoyancy force, and when further increase in velocity, when the particle will leave its stable state, at that time particle will start moving with the fluid. So bed will start expanding. So here you see, when we consider the bed height, up to certain velocity the height of bed will remain as it is till all forces become equal, and then it will start expanding. So when it comes to the fluidized state, you see the bed height will keep on increasing, and bed height will keep on increasing. When we observe the pressure drop condition, pressure drop will increase, but it will not increase significantly. You see, once all forces becomes equal, pressure drop will become almost constant. So when we increase the velocity, and when that velocity appear where bed will start expanding or particle will be at fluidized condition, we call that velocity as minimum fluidization velocity or incipient fluidization velocity. This concept we will discuss in detail further. Now we will discuss few important facts about the fluidization, such as the fluid velocity at which this motion of particles just starts is called minimum fluidization velocity, that we have already discussed in the last slide. Further increase in velocity causes the particles to separate still further from one another. So once we have we will achieve the minimum fluidization condition where particle will coming into the fluidized state, and further increase in velocity will separate particle from each other, although the pressure difference remains approximately equal to weight per unit area of the bed. So you see, once the fluidized condition is achieved, and further we increase the velocity, particle will start moving from each other, and at that time the pressure drop in the bed remains almost constant. So you see this figure here, there are different conditions where bed expansion is shown. In first condition, when we are considering bed at static position, when gas passes through it, till that point the bed will be at static position, and it will have a minimum height, or it will have a constant height. Now when minimum fluidization state occur, at that time particle will start moving with the fluid, or we can say particle will be supported by the fluid, and then the bed expansion occurs. Now if you see third figure, what happens over here, we will further increase in velocity, and all particle, if you consider previous figure, that is figure 2, here few particles are joined together, but in figure 3 all particles are moving separately and few very less particles are joining. Further increase in velocity in figure 4, we have observed that particle will move with the fluid, and it will be at more fluidized state, and the bed expansion will keep on increasing in comparison to figure 1, 2 and 3. So, with this condition we call as fluid bed in good condition. Now, when we increase the gas velocity further, the particle will start floating with the liquid. It means it will all particles will be hanging in the fluid. So, that condition we can call as it is fluidized. So, that condition we call as particles are floating over the fluid. So, this figure 5 shows the floating bed. Further increase in velocity, you can see in figure 6 that particle left the bottom space, the bottom support where it was initially placed. Particle will leave this space and start moving upward entirely. So, if this condition occurs, in this condition we can say particle will be carried by the fluid, and this particular condition we can we call as pneumatic transport. This is very important as far as chemical process is concerned. When we have to carry the solid from one position to another position, pneumatic transport is important in that case, and which is done by fluidization. When the fluidization reach to that level where fluid support the particle in such a way so that it flows with the particle, it is particles are carried by the fluid itself. That condition we can call as pneumatic transportation as shown in figure 6. So, here we have different conditions of fluidization. If you want to study more, you can go through this web link. Now, we will discuss different types of fluidization. What are the different types of fluidization? Mainly it is categorized in two ways. First is the particulate fluidization and second is the aggregative fluidization. So, what happens when you see this figure? In figure 1, when gas or liquid flows through the bed and when velocity is less. So, when velocity is less, it will not start moving, particle will be at a static position itself. So, the total height of the bed, that should be denoted by Lm, that is the initial height of the bed. Now, further increase in gas velocity when drag forces will be equal to the apparent force of the bed, it will start expanding, and when it will reach to the minimum fluidization condition, it will carried by the fluid, it will be supported by the fluid, in other word. So, when that condition achieves, we resemble that. If that condition achieve, we can call the height of bed at that condition is the height of bed at minimum fluidization condition, and which is denoted by Lmf. Further, when we increase the velocity, now if you see third figure, here we have consider only liquid phase. In first and second phase, we have considered liquid as well as gas, but here in third figure we have only liquid. Now, once we increase the velocity of the liquid, the particle becomes distributed uniformly through the bed. If you see this, here height of the bed increases significantly, but in total height of the bed, particle will be distributed uniformly. It means it is not like collection of some particle are more in some spaces and less in some spaces. In this condition, it is uniformly distributed. So, when this condition achieves, the height of the bed is referred as Lf, and this particular condition is called as particulate or smooth fluidization. So, you see, when we increase the velocity of gas and liquid, after some time when fluidization will achieve, after some time when we increase the velocity of the liquid, not the gas but the liquid, the distribution of particle in total bed will be uniform, and that condition we call as particulate fluidization. It happens with the liquid only, and what happens with the gas when we increase the velocity further, that we will see in next slide. So, you see what is particulate fluidization? Particulate fluidization is when particles are fluidized with the fluid, but it will be uniformly distributed throughout the bed. That is called as particulate fluidization. So, with a liquid, the bed continues to expand as the velocity is increased, and it maintains its uniform character, with the degree of agitation of the particles increasing progressively. So, particle movement will increase progressively, but it will be uniformly distributed throughout the bed. So, this type of fluidization is known as particulate fluidization. It usually happens with liquid. It can happen with gas, but at lower velocity. Further, if you see this figure, in the first figure we have movement of gas. So, what happens over here when this happens after minimum fluidization condition achieved. After that, when we increase the velocity of gas, what happens? The bubbles are formed inside the bed. So, particle will not be uniformly distributed, but these are placed some more. The bunch of particle is placed in one position, and in some position there will not be any particle because of availability of the bubbles. So, you see here more when this bubble is formed. Why this bubble is formed? Because it consumes the excess air with it. So, when the bubble will keep on moving upward, because gas is continuously entering into this, the size of bubble will also keep on increasing, as you can see from this figure. So, when this condition is achieved, that bubbles are formed inside the bed, this condition we can call as aggregative or bubbling fluidization. It usually happens with the gases. With liquid, the particles are uniformly spaced, but in gas we have aggregative fluidization. Now, when we increase the velocity further, what happens? That some particles leave the total bed and start moving with the gas, and after some time they fall down. It will not be carried by the gas continuously, but for some time the larger, you can say the larger bubble, when bubble size is increased almost equal to the diameter of the column, if that size of bubble is achieved, then the few particles are carried away from the rest of the particle of the bed, and some gap is observed, as you can see over here, but after some time they fall down. So, if this condition achieved along with bubbles, when space is created where particles are not available and particles are available above that space, this condition we can call as slugging. And you can observe in figure 3 that gas or liquid high velocity when we have, so we can go for the pneumatic transport. Pneumatic transport is basically occur when we are considering gas as a fluid, not the liquid. But in that condition, particles will be suspended in the gas, and that will help to carry the particle from one place to another place. So, all these conditions will occur with the gas, and transportation will also carried out with the liquid, and that we call as hydraulic transportation, not the pneumatic. So, you see aggregative or bubbling fluidization occurs with the gas, and particulate fluidization occur with the liquid. So, here the fact which just we have discussed, that with the gas, however, uniform fluidization is frequently obtained only at low velocities, as we have already discussed, at higher velocities two separate phase may form a continuous phase, or we also call it a dense emulsion phase, as you can observe that these particles are collecting over here. So, these are making the dense phase or the continuous phase, and another phase is the phase created by the space created by the bubble. So, that we call as the lean phase. So, the fluidization is then said to be aggregative fluidization. So, here we have discussed two types of fluidization. In an early attempt to differentiate between condition leading to particulate or aggregative fluidization, so here you see we have discussed two types of fluidization, the particulate fluidization and aggregative fluidization. Now what happens what is the condition through which we can define that this is a particulate fluidization and this is the aggregative fluidization. To define this condition we have one dimensionless number, and that we call as Froude number. So, you see the Froude number, when we define, this is defined as UMF square by G into D. Now, what is UMF is the minimum fluidization velocity or the minimum velocity of flow calculated over the whole cross sectional area of the bed at which fluidization takes place. So, this is nothing but the minimum fluidization velocity. Diameter of the particle is denoted by D and G is gravity, acceleration. So, considering these Froude number, we can say that when Froude number is less than 1, the particulate fluidization occur, and when Froude number is greater than 1, aggregative fluidization occur. So, based on this Froude number, we can identify what type of fluidization is occurring in the process. Now, we have another criteria to see whether the fluidization is particulate or aggregative. So, we have another method, another approach, so that we can say that this is the particulate fluidization and this is aggregative fluidization, and the approach is Rice et al. 1958 and Romeo et al. 1962 proposed 4 dimensionless groups to characterize the quality of fluidization. Now, according to them, the dimensionless number they have proposed as n, which is equal to the Froude number, this is first dimensionless number, Reynolds number at minimum fluidization condition, that is second dimensionless group, and here you see the density ratio of solid and fluid, and then we have the ratio of height of the bed and diameter of the column. So, you see this is another dimensionless group, this is another dimensionless group. So, total 4 dimensionless group has been defined, and collectively it is called as dimensionless number n. So, you see how we calculate the Froude number, that we have seen in the last slide. Reynolds number at minimum fluidization condition, how we will calculate this, that you will calculate the velocity where fluidization will occur, and considering that velocity we can calculate Reynolds number, the densities and height of the bed as well as diameter, all factors we can calculate. So, we can obtain value of n. So, when n is less than 100, particulate fluidization occur, and when n will be greater than 100, aggregative fluidization will occur. So, you see when we have increased in number, the possibility of aggregative fluidization increase. Similarly, the same factor we have observed in last method, which is given through the Froude number only. So, when we see the value of Froude number or value of Reynolds number, all this has fluidization velocity in numerator. So, what happens when we increase the velocity, aggregative fluidization may occur. So, that aggregative fluidization can be observed when we increase the velocity. So, in that way we can by considering the Froude number as well as value of n, we can distinguish between particulate as well as aggregative fluidization. However, when you observe, then also you can see. Now, in many industrial applications, a highly bubbling fluidized bed is not desirable. It is due to the fact that since gas bubbles carry little or no solid particles with it and thus practically bypass the solid phase, the basic purpose of fluidization is not met. So, what happens, we usually do not consider or do not desire for bubbling fluidization or aggregative fluidization, because in that case the gas which has to pass through the bed, it will bypass the solid. It means when solid is available over here, it will bypass this solid, so that this solid will not come into the fluidized state and therefore fluidization will not met. Now, why we do the fluidization? For example, if I am having mixture of two different particles, so what we have to do, if we want to create a uniform mixture of these two particles, then it should be fluidized properly, but that cannot be achieved with bubbling fluidization, and that is why bubbling fluidization is undesirable in industrial cases. So, the fluid must be evenly distributed at bottom of the bed, and it is usually necessary to provide a distributor. So, what happens, for uniform movement of fluid through the bed, the fluid should pass throughout the bed, not from one portion itself. So, for proper distribution of fluid, we provide a distributor plate at the bottom over which bed stays. So, distributor is an important accessory in fluidized bed. Now, here we will discuss the fluidization characteristics, that is fundamental of fluidization. If you consider this curve, here we have, if you consider this graph, here we have bed pressure drop versus gas velocity. So, what happens when a fluid is passed upward through a bed of particles, the pressure loss in the fluid due to frictional resistance increases with increasing fluid flow. So, pressure loss will increase with increased velocity of fluid. A point is reached where upward drag force exerted by the liquid or by the fluid on the particle is equal to apparent weight of the particles in the bed. So, when this condition achieved, particle will start leaving its position in the bed and bed will start expanding. At this point, particles are lifted by the fluid and separation of the particles occur, and further increase in velocity, the separation of the particle increases and bed becomes fluidized. So, you see what happens when we consider the fluidization, as we have already discussed previously, that when drag forces will be equal to the apparent force, the particle will start leaving its space, and when the separation of the particle from each other occurs, at that condition the bed becomes fluidized. So, we have to discuss the nature more carefully, nature of this graph more carefully. So, what happens initially when we increase the gas velocity, pressure drop increases. Pressure drop increases till all forces become equal. So, when we consider this graph and when we observe zone O to A dash, this line or this zone shows a static bed of particles for which plot is straight. You see here static bed we are considering, it means till here bed is not coming into the fluidized state. So, porosity of this bed remains constant even if fluid velocity is increased, because till all forces become equal, then only it will come into the expansion state, and till that the voidage or the porosity of the particle, porosity of the bed becomes uniform or becomes constant. Further, at point A dash, the bed becomes unstable and minor movement and adjustment of particles begin to take place to offer maximum cross sectional area for fluid flow. Now what happens in A dash when the particle will start leaving its space? So instead of a uniform voidage, the voidage increases, and it may happen that the fluid may be passed through complete cross sectional area of the bed. So instability of the bed continues as the fluid velocity is increased until at point A the loosest arrangement of the particle is established. So you see, at point A the particle will start losing its arrangement, and at point A the bed becomes fluidized, or this is the condition where minimum fluidization, this condition we can call as minimum fluidization condition. Now from point A the bed begins to expand with increasing fluid velocity since the porosity of the bed increases. So at point B, you see the point B is available over here. At point B fluidization is complete and all particles are in motion. So at point A particle will start moving, or loosest particle will start losing its arrangement, and fluidization starts over here. But at point B the complete bed is at fluidized condition. So beyond point B further increase in velocity can be obtained by relatively slight increase in pressure drop. So here you see, from point B when we increase the velocity, because all forces becomes equal over up to all forces becomes equal on the particle, and when we further increase the velocity the pressure drop will not be observed over here, because drag force is already equal to the weight of apparent weight of the particle. So from B to C slight increase in pressure drop is observed, but that is very less. So it requires to overcome the increase in frictional losses between the fluid and walls of the column. Consequently, pressure drop remains essentially constant with increase in velocity from point B and C. So this is the whole profile for pressure drop as well as fluid velocity, and we can observe from this, we can draw this graph with the experimental data, and then we can see, we can calculate what is the minimum fluidization velocity experimentally. So the force balance across the fluidized bed dictates that the fluid pressure loss across the bed of the particle is equal to apparent weight of the particle per unit area of the bed. So total balance, when we want to do, it should be like this: pressure drop equal to weight of particles minus buoyancy force on the particle, and that should be divided by bed cross sectional area. So when we are putting values over here, you see pressure drop is minus delta P into A, that is bed cross sectional area, into AL 1 minus E rho S into G. What is AL? Is the total volume of the bed. A is the cross sectional area and L is the height of the bed. So this is the volume of bed. 1 minus E is the solid section. So AL 1 minus E is total volume of the bed, and when total volume of the solid in the bed, and when we multiplied this with rho S, it will give mass of the solid into G. So that would be the weight of particle, and similarly we can define buoyancy force on the particle. This is the volume of bed. 1 minus E, that is volume of solid, and that we have multiplied with rho, that should be of fluid. Now if you consider the buoyancy, it will consider fluid with the same weight as that of the particle. Therefore here we have with the same mass as that of the particle. So here we have volume of the solid into rho, that should be the mass of liquid into G. And further simplifying this equation, we can have pressure drop during fluidization condition is equal to L 1 minus E rho S minus rho into G. So here we have discussed the fundamental characteristic of fluidization. We have defined fluidization. We have considered different. We have discussed different type of fluidization. So we are stopping this lecture 1 over here. We will continue the fluidization in lecture 2. So that's all for now. Thank you.